Okay, my goal is to stay under 10 minutes, and it takes a while to process this, and then I'll post it up on YouTube. All right. So uh, here we have three charges, and important. These charges are in three space. Okay, they're out in our space. Draw these three charges on your paper 4 times. So that is, there are going to be 4 different scenarios. Then draw two-dimensional cross sections of three-dimensional closed surfaces. All right, so that's the point here, is that we have to imagine they're in space and they're being enclosed by surfaces. All right, enclosed surfaces through which, in case 1, the electric flux is negative Q over epsilon naught. In case 2, the flux is electric flux is positive Q over epsilon naught. In case 3, it's positive 3Q over epsilon naught. And in case 4, it's positive 4Q over epsilon naught. So Gauss's law states that the net flux through a closed surface is equal to the charge inside the surface over epsilon naught. All right. Okay. So for any closed surface that encloses a total charge Q sub n, the net electric flux through the closed surface is Q sub n over the net charge over epsilon naught. All right, so here we have our three charges in space, and we need to have minus the net flux be now what? Okay, minus Q over epsilon naught. All right, which way is the field going? Right, which way is the field going? Right. Uh, because it's a minus charge, it's going in. All right, and so the idea is you have these three charges in three space. Pick any shape you want that encloses only that middle charge, and then there's the flux. That's it. So it can be blobby, and it could be a sphere, it could be a cube, it could be an icosahedron. It doesn't matter as long as it encloses only that one. The second one is going to enclose the middle and the bottom one, so that you have one minus charge and two positive charges, giving a net one positive charge. And again, it doesn't have to be spherical or elliptical. It can be weird as long as it's closed and encloses that. If all three of them are enclosed, then the net charge is right. Net charge is 3, positive 3. And then if it's kind of a roundabout thing, some way to exclude that minus 1 charge, then you're going to get 4Q over epsilon naught. And so I would have done this one, and then if we'd been in class, your job would be to repeat this, 3 charges, draw these charges on your paper 4 times, then draw two-dimensional cross sections of three-dimensional closed surfaces through which the flux is, and then there's some various conditions there, right? So if you just have some sort of flux around or some closed surface around the first one, then it's plus 2Q. How to arrange it to get plus 1, you got the 3 plus 3 and the minus 2. How to get 0 is to then have some sort of, dog bony shape, something like that, something weird, and you get plus 2 and minus 2, and then to get plus 5, we have the plus 2 and the plus 3. The point is this: if you want to know what the flux is, what you really need to know is what is the net charge enclosed. Now, another piece that's important is if the net charge is positive, the flux is out because the field is out. If the net charge is negative, then the field is inward at each point, right, at each point. The electric field strength just above one face of a copper penny is 2,000 newtons per coulomb. What is the surface charge density on this face of the penny? Well, here's a penny, here's the field. The penny is a conductor, right? So the excess charge on a conductor resides on the surface, and we know that the electric field on the surface of a conductor is equal to the charge density over epsilon naught, and that is going to be perpendicular to the surface, so we get our charge density by substituting in the appropriate numbers. And yeah, 1.8, right? The 2,000, I'm going, that's just two significant digits. And again, it's so much easier to just write 2.0 times 10 to the third, right? So the point is that the point is, if you go back to the first video, right, the using Gauss's law allows us then to understand what the field is, like, or the charge distribution. It allows us to calculate other quantities, not just flux. So there we have the charge density. The next question is, how do you get a spark plug to work? Well, you've got to get a field strength up to a certain critical level, and then you would have that happen. And so what kind of minimal surface charge density is required so that the field strength is at least 3.0 times 10 to the 6 newtons per coulomb? So what we have is then the charge on a conductor is on the surface, so we need the surface density, and we're going to then again use that consequence of Gauss's law and say that the field at the surface is the charge density divided by epsilon naught, and we can then solve for epsilon naught. So we get a sense of how much charge per meter squared we need. Yeah. And so there's that. And I think that's it. That's the last one.